Good afternoon and welcome to today's HydroCAD webinar. My name is Peter Smart. I'm the developer of HydroCAD. I will be the presenter this afternoon. And for today's session we're going to be talking about modeling pipes in HydroCAD. There are a lot of different options for pipe modeling, and so this sometimes creates some confusion as to what the best solution is for modeling a pipe in HydroCAD. But we're going to look at those different options and when it's most appropriate to use all of those in a given situation. What this highlights is one of the important aspects of HydroCAD, that it is a set of modeling tools, and rather than just throwing every physical detail of your site into the model, you do need to consider the role of each site, and in this case a pipe, and decide what effect is that going to have on the water flowing through it, and what are the objectives of my analysis. And you really need to look at those two questions in order to determine the best way to model that pipe. So you can't just throw the pipe in and expect to magically get the correct analysis. It is a set of hydrograph, runoff generation, and routing tools, and you need to pick the appropriate tools depending on your specific requirements. And essentially the objective of today's session is to talk about those different options pertaining to pipes so you can make the best decision as to exactly how you want to include the pipe in your model. So the material that I'm going to discuss today can also be found, at least the basic info, on our website. If you go to hydrocad.net and click on support, you'll find a document on modeling pipes and culverts, and that will give you the basic outline of the different techniques that are available to you with links to each of these options. Very roughly, what we're going to talk about, the options are modeling a pipe segment as modeling a pipe as a flow segment within a subcatchment, essentially treating it as part of the travel time or time of concentration. That is the first option. We're then going to look at reach routing, essentially to treat the pipe as a reach and model it using reach routing techniques. Then we move on to modeling a pipe as a culvert outlet, which will do a full culvert analysis as opposed to just the open channel flow analysis that we would get within a reach. Then we'll look at inlet conditions on pipes and how they may affect the flow, impoundment of water or storage at the pipe inlet, situations such as culverted road crossings. And then we're going to move on and look at storm sewers and the different options for modeling storm sewers and how you would handle tailwater in those situations as well. So that's the rough overview of what we're going to look at today and the progression. So let's start by looking at a pipe modeled as a flow segment within the time of concentration. I have a sample project that I've got set up here today. And excuse me just a second, I want to make a copy of this before we start. I have a sample project in which I've already got some data set up just to make this session a little bit quicker. I will try to do most of this live as we go along, but just as a fallback I have some examples that already exist. So to start, I have a single subcatchment where I'm including a pipe as part of the time of concentration. So if we edit that subcatchment and go to the TC tab, you can see we have three flow segments. I have a segment of sheet flow, a segment of shallow concentrated flow, and then a segment of pipe flow, which is actually being modeled as channel flow. And the first thing you'll notice is the relative TC that's being contributed by each of these flow segments. Let me cancel the editing window and double-click that subcatchment to bring up a report window. And let's look at the summary. And if we come down to the table here for the time of concentration, here we can see the relative contribution, the 17 minutes for sheet flow, 14.5 minutes for shallow concentrated, and 2.3 minutes for the channel flow through this pipe. The important thing to notice is that in this case the channel flow or the pipe flow is a relatively small portion of the overall TC. It's about 2 minutes out of 34. And this is despite the fact that we have here 1,000 feet of pipe length versus 1,400 feet roughly of shallow concentrated and 100 feet of sheet flow. So the channel flow is contributing a relatively small portion because its velocity is generally fairly high in relation to the sheet and shallow concentrated flow. So this is one option that you can use for modeling a pipe on your site. This would be appropriate if the only flow that's going through this pipe is the runoff from this particular subcatchment. So essentially the pipe is within that subcatchment and contributing to the travel time down to the point of analysis. When you use this technique, another thing you want to look at is you want to compare the capacity of that pipe that's being reported versus the peak flow, the runoff that's actually coming off that subcatchment. This will give you a rough check that your pipe is in fact adequate size to handle the flow that's coming off that subcatchment. Sometimes a question will arise about setting the actual flow depth, because what this analysis is doing is it's taking, assuming that the pipe is flowing full, and using that in order to determine the capacity and in turn the velocity for the TC purposes. In practice, your pipe is not going to be full, and in fact the depth is varying, but the velocity in the pipe, which is what we're concerned with here, does not vary that significantly as the depth does. You'll find that it's more a function of the slope and the Manning's value. And so whatever variations you may have are fairly small, and again, that's a small part of the TC. So usually we're not concerned with those specific variations in depth when we're modeling the pipe as a segment within the time of concentration. In order to get a more detailed analysis, there are other techniques we can use, as we're about to discuss. But this is the simplest technique. Again, it only applies if the pipe is adequately sized so that the runoff can pass freely through the pipe. If there is any restriction at the inlet, such that there's any kind of ponding, then you really want to use a different technique for modeling this. This is one approach largely used to support the TR55 TC option for channel flow segments, and amongst the channel flow segments that we offer in HydroCAD is a pipe channel. So that is the first of the options. Just to review, you probably will not use it that often, but it is available to you. If we double click that subcatchment, we of course get the runoff results in the hydrograph, and I'm going to put that graph aside for just a moment. We're going to look at that in a minute, and I want to compare it with some of the other options. So the next alternative is to take the same subcatchment and just remove the segment of pipe flow from the TC calculation and insert that pipe as a separate reach sitting downstream. So if we double click our subcatchment now, we have a slightly shorter TC because we've eliminated the segment of channel flow for the pipe. So we just have 32 minutes versus 34 for the TC. And so our runoff has increased slightly. We have gone from about 24 CFS to 25 CFS because of that reduction in the TC. Then what we're going to do is we're taking that runoff and we're running it through a reach. If we edit this reach, we have specified that this is a pipe, and it's a 30-inch diameter pipe, a circular pipe, same length of 1,000 feet with the same slope that we used before of 1%, 0.01, and a Manning's of 0.015. If we double-click the reach in order to open up a report, we get a reach routing calculation, and at the moment, you see we're getting a slight reduction in the peak flow due to the reach routing. We have 25.3 CFS coming in and 25.16 going out. So this 1,000 feet of pipe is providing some amount of storage and delay and attenuation of the peak. We could compare this to the original subcatchment that included the flow segment, and we were getting 24.14 with the pipe segment included. If we do the analysis with a separate reach routing, we're getting 25.16. So there is a difference in the results. They are different techniques that we're using to account for the pipe. But we do see some effect here due to that length. But you'll notice that it is not a great reduction in the flow here. In fact, it's pretty small. We're getting about 0.2 CFS out of 25. So we're getting about 1% reduction for this 1,000 feet of pipe. There's very little restriction in a channel of even 1,000 feet of length, and so usually it has a relatively small effect on the attenuation and peak delay. Of course, as we reduce the slope or increase the Manning's value, that will get greater. But at the moment, I just want to show you a comparison between these two different scenarios. Now, modeling a pipe as a reach is only appropriate if that pipe is operating under open channel flow. You want to remember that a reach is always for open channel flow. It does not apply if we have a restriction at the inlet so that there's any ponding, or if we want to consider energy losses at the inlet. Both of those situations require us to do a full culvert analysis. And the way we do a culvert analysis in HydroCAD, moving on to our next example, is we actually set up a pond with a culvert outlet. And we're doing now a more complete analysis of the culvert. So we have the same subcatchment runoff up top, but now running into a pond. Let's edit that pond. And what we've done here is we've selected the catch basin option. What this does is that it specifies that there's no significant storage in this pond. It's a zero storage pond. This option is often used for a catch basin. The advantage of this over specifying that you have 50 or 100 cubic feet of storage is that you get a more stable routing to essentially neglect the storage completely. And that's what the catch basin option does for you. When you pick catch basin option, you will get a tab for defining your outlets up top, but there's no tab here for storage. The storage tab would only appear if we pick the detention pond option down the bottom. So looking at our outlets tab, we have one outlet device, which is our culvert. And on the culvert screen, we've specified essentially the same parameters that we had used before for the two previous alternatives for modeling this section of pipe. There are a whole bunch of different geometry options here for pipe. We can even put internal fill inside the pipe. That's a feature that was added in 9.1. And we can do arch and elliptical pipes. So there's a bunch of other options here. But the issues we're talking about today are the same regardless of what shape or internal fill you may use for the pipe. Now, you can manually enter this culvert to match. That is to match the reach that we've already set up. But there are a couple of other options you should be aware of. For example, we started by setting up the subcatchment running into a separate reach. And what we could do is we can actually right-click a reach. And if that reach consists of a pipe, then you're going to see an option, Convert to Pond, is going to appear in that right-click context menu. And it's going to ask you to verify that you actually want to do that conversion because you cannot reverse it. We click OK. And it's now created a pond for us, a zero storage pond, and created an outlet device with all of the same, a culvert outlet with the same parameters as the reach. So that's a very easy technique if you've already set up a model where you have pipe reaches and you want to flip those over and look at an alternative of pond with culvert outlet, just right-click and do Convert to Pond. And that's exactly what I did in order to get this next node in my example. Now what I want to do here, I actually want to go back. So I'm going to close out of this project and just go back to my original. So I get the unconverted reach. So this is the result that we got when we did a reach routing. And now next to it we can do the pond with culvert outlet alternative. The pond with culvert outlet has no storage in it. We need to remember there's a zero storage pond, and unless you have storage in a pond, you are not going to get any attenuation in the peak. What the quote pond node is going to do for you is it's going to determine what the actual headwater is at the inlet of that pipe. So you'll notice here that we have a peak elevation that's being defined of 3.09 feet, and that's actually a depth in this case because I've set our pipe inlet invert to 0. So we have approximately 3 feet of head that's needed in order to push that 25.3 CFS through the pipe. So that's essentially that's the critical piece of information that we're getting from this analysis. If we were to look at the reach routing for the comparable situation, still a 30-inch pipe, the reach routing is not looking at the inlet. The reach is looking at just Manning's flow within the barrel of the pipe. So if we had a very well-rounded or tapered inlet so that we had no restrictions and we could get everything into the pipe, in that situation, this might be an appropriate analysis, because you'll notice we're getting a flow depth of about 1.5 feet in that 30-inch pipe. Whereas the culvert analysis is telling us that we're actually going to have about 3 feet of depth at the inlet before that pipe. Now that depth at the inlet is going to be influenced substantially by the entrance loss coefficient. If we go to the summary for this pond, here we have our 30-inch culvert, and we have a K sub E parameter, which is the entrance loss. There is no entrance loss parameter when we do a reach analysis. This is only available to us when we do the culvert analysis. And a K sub E of 0.9 is a relatively high energy entrance loss. That corresponds to something like a square-edged projecting inlet. If we edit this particular culvert, here's where our K sub E value is specified. So a corrugated metal pipe projecting with no head wall would give us a K sub E of 0.9. We could do a corrugated metal pipe mitered to conform to fill, and now we get a drop in the K sub E. Or if we went to something like reinforced concrete pipe with a, let's see, a groove end with head wall, then we get our K sub E down to 0.2. So this energy loss coefficient varies quite substantially. So if we change our K sub E from 0.9 down to 0.2, as we've done in this case, then when I OK this description, we want to have a look at our results. In particular, our peak elevation here was 3.09. If I OK this, our peak elevation comes down to 2.12. So we've significantly reduced the headwater at the entrance to this pipe by reducing the energy loss at the entrance. So that is one of the principal reasons why you will see a difference in your results between a pipe reach and a culvert outlet. The culvert outlet is including an energy loss coefficient, which is not being considered in the pipe reach scenario. Also, in terms of elevation or depth reporting, keep in mind that a reach is reporting the depth within the reach. That's all it's looking at is Manning's flow within that body. So that's a flow depth. Whereas when we do a culvert and pond analysis, the elevation that's being reported is the elevation in the pond, which is the volume of water in front of the pipe before we enter it. So they're slightly different. This isn't actually telling us the direct depth within the pipe. That's a different calculation, the depth of flow. The pond analysis is telling us the headwater depth at the inlet. So this is the next option we have, which is to use a zero storage pond with a culvert, and now we're including inlet losses. Now the next scenario I want to have a look at, what happens if this pipe is undersized? And I want to look at two different situations, both the reach and then the pond with culvert outlet scenario. What I've done here is I have just increased the inflow area so that we get a larger peak flow coming into this pipe. And again, this is just a pipe reach that we're looking at. And what you'll notice in the hydrograph is we have this flat-topped outflow hydrograph. And we have a warning message which has occurred. So here's our flat top right here, and then down in our message box we have this warning telling us that reach 4P has attained 0.97 acre-feet, pond with culvert advised. What that message is telling us is that this pipe reach can no longer pass the specified inflow of 25 CFS based on Manning's equation. Manning's equation is only allowing us to pass approximately 20 feet through that pipe. When we exceed the 20 CFS Manning's capacity of the pipe, the software doesn't have any information on how to handle that excess. Hence this warning message, and it's telling us that it's taking the excess volume and simply detaining that at the inlet and passing it through later on after the peak subsides. Let me flip this hydrograph to a 2D view and then zoom in. If I drag from upper left to lower right, we can zoom in and we can get a bit closer look at what's happening. The green curve is the inflow hydrograph and the blue is the outflow, and the blue is being limited at the Manning's capacity. You will notice there's a little blip here on the outflow. What's going on there? Well, what we're actually seeing is that the capacity of the pipe is actually greater just before it's completely full. When there's a smaller wetted area, we get a slightly higher capacity. So the flow goes up and then the pipe fills completely and it comes back down to the full pipe capacity. If we go to the discharge tab up top, we can see that curve for a pipe. And what we're seeing is our highest capacity is occurring just before, if I can zoom in there, our highest capacity is occurring here at 1.88 feet of depth. Then as we go above that, the capacity actually decreases. So that's why we're seeing that little spike at the beginning. After the spike, we get a flat top, a constant flow, and the software is detaining that additional volume at the inlet and then passing it after the flow subsides. So that's why this flat top is extending even after the inflow decreases. Then it's finally able to pass the flow through the pipe, and then the inflow and outflow correspond for the remainder of the routing. So that's the effect we're going to get. The red warning is there because it's telling us this isn't a physically realistic situation. It's detaining that, but in reality it should be creating some kind of pressure on the pipe, some kind of headwater, which will influence the discharge, and also the fact that this pipe breach is not considering the entrance loss. So there are a number of reasons that this is not really a valid representation of the physical situation, hence the red warning message. So what do we do about this? Well, as the message is advising, we should change this to a pond with a culvert outlet. Now, with any of these messages, please remember, just click the message for additional detail, and that will give you specifics. It says a pipe breach is filled with water, causing the flow to be limited and the excess volume to be detained without head. The calculations which assume normal flow are not being altered to handle this. It's up to you to use a different situation, such as a pond with a culvert outlet. So it's very important that you do review all your messages, and particularly the red warning messages need to be resolved. The red messages are telling you that some assumption of the model has been exceeded and the results probably are not valid. So before you start looking at those numbers and jumping to conclusions or emailing support and saying this result doesn't make sense, you need to look at the warnings and in general follow that advice and resolve those warning messages. You'll find once the warning's been resolved, then you're going to get physically realistic results from your model. So in this situation, what we need to do is, rather than using the scenario of a pipe reach, we need to go back to our pond with culvert outlet situation. And this is a direct conversion. We again could do a convert to pond, and that's basically what I've done here. Another little trick that I used in order to set up the sample, if we want to make a copy of these nodes, we can just do a control drag. Actually, my problem here is I need a little more space, so let me just move these over. By the way, to select a whole bunch of nodes, I dragged a selection rectangle right over the whole group, and then I can move them as a unit. And in this particular file, you'll notice I have a grid behind. If we go to Settings Diagram, I have specified that I do want to show a grid and that I want to snap to the grid. And I've set a grid size of 1 unit. So that's how I have this background that you're seeing with the snap behavior. So in order to make a clone of a node to look at a different scenario, I could hold down the control key and drag, and that gives me an exact copy of that subcatchment. We could do the same on the reach, and then we could move the routing over. So now we've made an exact copy. And then we could right-click and do Convert to Pond and say OK. And that's the exact process I used to create this pair of nodes in our example. So let's just get rid of that one for the moment so I don't confuse myself. So now we want to compare our undersized pipe reach with the similar situation as a pond with a culvert outlet. If If we double-click that pond and open up our report, again, remember we have no storage in this pond, so our outflow, peak outflow is the same as the inflow. But we do now have a complete culvert analysis that's being performed, so we're able to determine the peak elevation that is going to be needed here in order to basically force that water through the pipe. So it's telling us that our peak is 104 on top of this 24-inch culvert. I believe our inlet invert is 100 feet, so this is 2 feet of head approximately, or 4 feet over the invert, 2 feet over the crown of pressure that's being applied at the inlet to this pipe. That's what's necessary to actually push the water through the pipe. This might be a catch basin, for example, where we have a very small amount of storage, but we are able to develop that amount of head. If we look at the stage discharge report, here's our curve for the culvert, and again you see the little hook, the reduction in flow as the pipe is completely full, and then greater flow as we have pressure flow, head occurring over the inlet. You may notice that even though this is a 24-inch pipe, that the crown is at 2 feet, that little hook is occurring somewhat higher. Well, that's because this stage discharge report is the depth in the pond, in front of the pipe. It's not the depth inside the pipe. So that's why the hook is occurring at a slightly higher depth. It's taking about 2.5 feet of water, about 6 inches over the crown, before we fill the pipe completely, and this little hook occurs. So again, there are differences between the reach and the pond scenario that you'll see. So this is the routing through the culvert outlet. Coming back to the summary, you can see we've got a 24-inch culvert, and we have more or less average energy loss of 0.5. We could see the effect of different entrance energy loss values. So for example, if we go to the outlets and edit that, and let's just manually change our energy loss to 0.1, and when I click OK on that, we want to look at this peak elevation of 104.19, which drops to 103.78. So we've lowered the headwater as we've provided a more efficient inlet. And at the other extreme, if we change that K sub E value to 0.9 and click OK, then we jump up to 105.5. So you can see the different headwater that's going to be necessary based upon that energy loss at the entrance. Okay, while I'm doing it, someone asked me to have a look at the other hints that were appearing in the message box. I looked at the warnings, which are in red, which are critical messages. You really must address those. The yellow hints are less severe conditions. You certainly want to be aware of what's going on there because they are situations that you may cause changes to the model. So for example, 37 is telling us that a longer time span is advised for full volume. What's going on here is it says that the calculation time span may not be long enough to encompass the entire hydrograph duration. This may cause the reported volume, depth, and detention time to be less than the true values. Peak flows are generally not affected. If we look at the hydrograph and switch to a 2D view, one thing you'll see here is that we still have a non-zero flow down here at the very end of the hydrograph. That's the truncation that's being referred to in this message. So that the reports are telling us the volume under this curve, but they're stopping at the 20-hour mark. So if we want to get complete volumes coming out of this pond, we need to increase the time span in order to resolve that message. We're also getting a hint concerning the peak elevation. In this situation, we haven't defined any storage for this pond. It's a zero storage pond. And neither do we have an overflow of a weir or grate. So there's no way for the software to know whether this peak elevation is a problem for us or not. So what it's advising us to do is actually go back in and edit that node and at least put in a flood elevation. So if we put in a flood elevation of 106 and click OK, that hint now goes away. We've told the software 106 is the next critical point we need to know about, but our elevation since our elevation is just coming up to 105.5, it's less than the peak, we're okay, so now that hint disappears. So that's what that hint is. It's just encouraging us to put this flood elevation in, so now the software can monitor the level in that pond and automatically notify us if we get to a situation that may require a change in the model. So we're looking here at just, again, an undersized pipe. We're developing a certain amount of head that's necessary in order to push that flow through the pipe. The next scenario we might want to consider, a couple of scenarios, is that we might have storage at the inlet of that pipe, and we might also have an overflow device. So for example, if this were a culverted road crossing in this entire scenario we've been looking at, we start by finding out that our pipe is oversized, and so rather than doing a reach routing, we use a pond with a culvert outlet, and we find that a certain amount of head is necessary. Now, since we're generating have a foot or two of head over the crown of the pipe, if this is in a catch basin, the storage is probably negligible and our model's fine. But if this is a culverted road crossing such that we have an area that's being flooded, then we may be impounding a significant amount of water at the inlet of that pipe. So in that situation, what we probably want to do is define the storage at the inlet. So coming over to our summary now for this modified pond, we have the same culvert outlet that we were using before. Those parameters are identical, but we've now added the storage. So we've got one storage volume, which is the prismatic storage option, and it's custom storage, and we have defined a surface area at several different depths. And based on that, the incremental and cumulative storage is being calculated. So if we click on the storage tab up top, here in blue we have the stage storage representation for this area where we're impounding water. And so because we have storage defined, we are now getting a reduction in the peak flow as we route through this pond. So our 25 CFS coming in is actually being knocked down to about 22 CFS based on the storage. If we flip to a 2D view, you'll get a slightly better look at that. There's our peak inflow and our peak outflow. Also interesting, you notice we have two little hooks down here in the hydrograph, and as I explained before, that's the behavior just before the pipe is completely full. So we actually have a slightly greater flow, and then the pipe became full and the flow was reduced, and then head developed on the pipe. So that's what those little hooks are. And so here you see the reduction due to the storage, and we have now knocked our peak elevation down from, I think, about 105 feet to 103 because we're allowing for the storage, and approximately 4,000 cubic feet of water is being stored in order to cause that peak reduction. So this illustrates that when you have a roadway, a crossing like this, it's useful in many cases to put in that storage around the culvert inlet because it can have a significant effect on your routing. It may reduce the flow, even if it's just a couple of thousand cubic feet of storage, maybe a couple of hundred square feet that's being inundated. Then the detention and attenuation effect can be significant. Now, the next thing that might happen to us in this roadway crossing is we might also have an overflow situation. We might have a road that's overtopping. So actually, let's keep this one open. And we've been looking at a 25-year event in this particular scenario. Let's increase that to perhaps a 50-year event. And now we've got a bunch of different warning messages that are appearing. We've exceeded the storage range is the first message that's coming up. So we've defined a certain number of feet of storage, and that's completely filled. And now the software doesn't know what to do because we've exceeded that. The overfilled storage can trigger a number of other conditions. For example, we're getting oscillations. So we're getting an oscillation warning in this case, and this in turn can cause us to get an outflow which is slightly greater than the inflow. So here you see three warning messages pertaining to this one pond. This is actually a very, very useful scenario. And there are a number of different things you might want to investigate to try to resolve this, and each of these warning messages is going to make certain suggestions. The second two are suggesting that you look at your time step, your main routing increment, that you may want to use a smaller time step, and also perhaps a finer routing interval. And those parameters are on your calculation settings screen on the time span tab. And we've already got a fairly small time increment of 0.01. We have a default finer routing of 1. What the finer routing does is essentially it takes our time increment and it divides it by that number of intervals and uses a smaller increment internally to do the routing through that pond in order to attempt to get a more stable routing. So if we use a finer routing of 2, then our internal increment is actually going to be 0.005. It's going to divide that in half. So we could bump up the finer routing to try to resolve this. But we want to look at all of these messages and note that we also have a storage range exceeded. And that is often the problem that's triggering this set of messages. So if you're getting oscillations or Q out greater than Q in, also check and see if there's storage range exceeded. Because what's happening to us is we are essentially hitting the roof on this particular pond. Let me switch to the 2D view. And a couple of things here. We can zoom in, and here you can actually see the oscillations. So when you get an oscillation message, do have a close look at the hydrograph. Try to see where those oscillations are actually occurring, and that will give you some insight into what you might do in order to resolve them. You can also see we have this funny shift here in the curve. Let me do another useful thing here. If we right-click the hydrograph and go to Report Items, select Elevation, we can now enable an elevation curve on this graph. So we have our inflow and outflow curves, but we also have elevation. Now we need to zoom in a bit to see what's going on. This is getting a little more confusing to see. This black curve is our elevation, and we're looking at our summary. Our storage is going up to 104. So at 104, let me put a line across there. So here at 104 is where we're filling our storage. And you'll notice that's where the trouble begins. The storage is completely filled, but you notice that the elevation is still increasing, the black line. What's happening here is we're pressurizing that storage. It's being treated essentially as an underground storage tank because we haven't told the software what to do once we get above 104. So it's not going to make any assumptions about where to store that additional water. As far as it's concerned, there's no additional storage. And so it becomes pressurized. When it becomes pressurized, things are getting less stable. So this scenario might be appropriate if we actually had an underground tank and there was no storage above 104. But in reality, there tends to be some additional storage as the level increases. So that's what we need to look at in this particular situation. So there are a couple of things we could do. One of them is we could define storage above the 104 mark. So let's edit this pond and come back to our storage, and we need to specify that up at 105 we've got 20,000 square feet of surface area. Now let's click OK a couple of times. We've resolved all the red warnings. So we've just given the software the information about how much storage is in that next foot. And by doing that, the water's able to rise a little more and spread out a bit further so we can get a complete routing calculation. And let me just clean up this graph a little bit. Let's just remove that elevation curve. So now we're back to an inflow and an outflow curve with no warning messages. So that's a pretty good example of a common oscillation situation and the importance of defining the storage as high as is necessary to complete the routing. Now, let's say that our roadway crest, our crown of our road, is actually at 104. And so you tell me, well, the water can't go up to 105. It's just going to spill over the road. Okay, there's two things we then need to do. The first of them is we want to put in a suitable overflow device for the crown of the road. So at perhaps 104, we would come in and edit this pond and go to the Outlets tab. And for simplicity, let's just put in a sharp-crested rectangular weir, and we'll indicate that it's at 104. And put a description in so that you and your reviewer know what you're actually doing with this particular device. Let's put in roadway crest. And then we have a crest height, which is used to adjust the weir coefficient. This is the height above the approach channel. So this might be 4 feet in this case. This might be the height of the crown above the adjacent depression, the low area at the culvert inlet. And we want a crest length, of course, let's say 20 feet. And I'm not going to get into the other weir parameters at the moment. You can click Help if you want more detail on those. And let's click OK a couple of times. And we've modified the result. There's one thing I forgot to do. Let's go back in and edit this and go to the Outlets tab. And I have two outlet devices, device number 1 and number 2. They're both routed to primary. It would be very useful here to know how much water is going through the culvert versus how much is going over the road. So let's edit that overflow weir and change the routing from primary to secondary. So now we have two separate routings. We click OK. Now we get an additional secondary outflow curve, which is in red on the hydrograph. So now we can see the more complete behavior of the system. The blue is the water going through the culvert, and then when we get up to the crown of the road, we start getting some flow over the weir, which is our secondary discharge. And then when we drop back below the crown, that goes to 0, and we continue getting flow through the culvert. So that's, although the routing is actually identical when they were both routed to primary, by using primary and secondary, we're able to split those flows, which is very handy for reporting purposes, and it tells us exactly how much is going over the roadway. Now, the next thing that's very important about this model, we have, let's go to the summary for a moment. So here's our culvert at 100 feet and our spillway crest at 104. It's very important here that even though you might think the storage ends at that crest of 104, we need to define storage to some point above the crest of the roadway. This is critical because as the water starts to flow over the weir at 104, the software has to know how much storage is actually available. Even if we're just 1 inch over that crest, how much storage is in that inch? And if we don't give that information, then the software is going to assume again that it's a closed storage volume at 104, and we're going to get storage exceeded message and possibly even oscillations and other problems. So we want to go up slightly, in this case 1 foot above the crest. And to do this, you would essentially just build an imaginary wall above your weir to come up to the next contour elevation. So now we take the area at 105 contour of what would be impounded. So this is the volume of water which would be controlled by the weir. So we're drawing that imaginary wall at the control point above the roadway crest. So once you do that, we get a reasonable routing. It's a very common situation that people will just define the storage up to 104, and then they have trouble because the water has to go a little bit above that, maybe just an inch, maybe a foot. But in order to get a valid routing, you need to include that additional storage. So that's a bit of a diversion from the initial topic just of pipe routing, but you can see how it leads into a bunch of other issues. That is the amount of storage you have at the inlet, how you manage outlet device, overflow devices, and making sure you've defined enough storage so the software can do an adequate routing as those overflow devices kick in. And so I've just done manually what was already set up in this next scenario in my predefined illustration for this session. I've just added that additional storage and an overflow device. So that's essentially that's the full range of options that you can use for modeling a pipe, from a flow segment within a subcatchment to a pipe reach to a culvert outlet on a pond, and then some of the more involved situations you may run into. The other significant issue related to pipes that I want to touch on today has got to do with storm sewers, because that's sort of the ultimate complication of this progression that we're looking at. That rather than just a single pipe, now we're looking at a series of pipes. And a common way to handle that in HydroCAD is to use a zero storage pond with a culvert outlet, and then to route one of those ponds directly to the next. And that's what I've illustrated in this particular example here. So we have a series of subcatchments, which are the contributing areas coming in along the side of this storm sewer network. And in this case, each of these catch basins and ponds is actually the same. There's no storage in these. I've got the same section of pipe with the same slope. And the way I created these, just to show you that trick, let me do a control drag on one of these just to give me another node I can work with without disturbing my original. and let's right-click and edit this, and we have just an outlet device, just the culvert. Now, if we make a copy of this to do a control drag for the next node in our chain, and then connect those two are absolutely identical. But in the second one, presumably the pipe is going to be somewhat lower. So we could go in and edit that, go to Outlets, double-click the culvert, and then we could change the inlet invert. One of the things we might want to do is to lock the slope here so that when we reduce the inlet, the outlet is recalculated accordingly. So that would be one alternative. But there's another trick you can use which makes this much easier. If we simply right-click that second node and select Raise and Lower and put in -1, for example, then it will drop that. All the elevations in that node will be reduced by 1 foot. In this instance, it's just reducing the outlet device. Both the inlet and the outlet of that culvert are being lowered. If we had storage or other outlets, then all of those elevations would be reduced. So everything related to that catch basin is being lowered in this instance. So that's the technique I use to actually do a repeated control drag, connect it, and then do a raise lower and put in -1, etc. So there are a lot of little tricks like that you can use. And of course you can put in a positive number in order to raise that back. So coming back to the primary topic here, which is this storm sewer system, we have a sequence of different ponds with no storage but with a culvert outlet. And let me just clean this up, and let's just get rid of these temporary nodes. And just to start, I'm going to disconnect that outflow by dragging it back to the catch basin. And I want to start with my 25-year flow and double-click this catch basin in order to have a look at what's going on. So we now have a runoff area going into this pond with culvert outlet, and there's no storage here at the moment, so we have a peak elevation that's being reported. So that's the headwater that's necessary to push that flow through the pipe. And we have, in this instance, I believe I'm using 50-foot segments of pipe with a slope of 2% in between these catch basins. So now if we add another contributing area downstream, and let's actually disconnect this one. So if we take this one and now route it downstream to another catch basin with a contributing area, let's just have a look at this peak elevation. I'm not sure this will change, but we'll see. The peak elevation is 100.8 right now because we have free discharge from this culvert. But if we run it into the next catch basin, then in fact the peak elevation here has increased. We're looking at the peak elevation upstream here in 10P. So it's gone up slightly because of the tailwater that's been generated downstream. Now, this has occurred because if we go to calculation settings, we are using the dynamic storage indication method to do our pond routing. Your default routing method is just the storage indication method. If we switch back to storage indication method for a moment, we're not running in, I'm looking at red warnings, we have a warning about early inflow, but we're not running into any other warnings quite yet, so we don't seem to have significant tailwater issues in the model at this point. But as we go on adding more nodes downstream, and if we calculate those, now we start to get a bunch of different warning messages that this pond 11P, which is downstream, is exceeding the water level in 10P above it. If we click that, it's explaining that essentially we have a possible tailwater dependency. So, but we are still using a routing procedure, the storage indication method, which is not able to respond to tailwater. So essentially the bottom line on this message is that we need to go into the calculation settings and we need to change the pond routing method. And generally, we would want to use the dynamic storage indication method. I do not recommend that you use the sim-route procedure, simultaneous routing, except for very specific applications such as flow loops. It is not as stable as the dynamic storage indication method, and so it's got much more limited applicability. So you should generally start with dynamic storage indication method, and that's your preferred technique when there's tailwater. So if I click OK on this, Now you'll see most of our warning messages actually disappeared. All of the tailwater related messages are gone. We still have a warning pertaining to the early inflow needing an earlier time span. We can fix that. The reason that's happening, I should explain. If we look at our subcatchment, in this subcatchment we have quite a high curve number of 98. And so when you look at the hydrograph carefully, you can see that at the very beginning of the hydrograph at 9 hours, there is still some flow. It's non-zero. So we're skipping that early inflow. And that's the reason that this message is saying the runoff depth is greater than 3.42 inches. It's calculating the total depth under this hydrograph, but it sees that there's some flow at the beginning and perhaps a little at the end that we're missing, so that the actual depth is somewhat greater than what it's able to calculate. So if we go to calculation settings and we change our starting time back to perhaps 0 hours and click OK, now you'll notice all of our red warnings have disappeared, because looking at our runoff hydrograph right here, we're now starting early enough back at 0 that we're getting the very earliest of the runoff. So the higher curve number meant that the runoff was starting earlier, and we in fact needed an earlier start time in order to capture that complete volume. Now if we still want our graphs to be zoomed in essentially on the peak, then we can go back to calculation settings, and rather than changing the time span, we could go to the reporting tab and we could indicate that the reports, the plots, and the tables actually go from 10 to 20 hours. So now our graphs are essentially zoomed in automatically, but the calculation behind the scenes is happening over a longer time range. Now we still have a message here about the runoff depth being a little bit greater, and that's probably because we need a longer calculation time span. So we need to run that out to perhaps 26 hours in order to get all of the runoff. Okay, so now we've got rid of that warning, and you notice the runoff depth is equal to 4.06. It's not just greater than 4.06, so we're capturing all of the runoff. And then if we come down and go back and look at the catch basins or culverts, we can see the water surface elevations that are occurring in this system. At our first catch basin, we've got a peak of 101.49. If we go down to the second one, we've got 101.36, slightly less as you'd expect. So the system is now automatically able to handle the tailwater that each of these catch basins is producing. The software also does a cross-check for you, and whenever we have adjacent nodes, it checks the water surface elevation in each node at each time step, just to make sure that what we believe to be the upstream node has a higher water surface elevation than the downstream node. If at any point in time that's not true, if there's a reverse head essentially at any point, then we will get a red warning message. So that check is being done for you. So you can be assured that there is a consistent gradient from upper to lower node that's occurring. Now we still do have a number of hints that are occurring in this model. These are advising us that we have flood elevate or peak elevations that are being attained, and it's advising us to put in a flood elevation. What this means is that the software has no way of knowing whether we've overfilled our catch basin or overtopped our roadway. It doesn't know what we're modeling. So we could put in a flood elevation in order to give it that information, or perhaps we might have an overflow device. Another situation that can occur in this kind of storm sewer is that you may come up over the grate, of course, and overflow. And in that case, then we might edit that particular pond, and we have a culvert outlet at 100 feet. We might also add an overflow, and perhaps we do this as, let's say, a horizontal orifice set up at 110 feet. So perhaps we use this to model our grate, just doing this very quickly. So now when we get up to 110, we'll get separate overflow through the grate rather than just additional pressure being applied to the culvert. So you need to include whatever elements are appropriate in the modeling of your storm sewer. We have a good article online on modeling storm sewers. I would advise you to have a look at that. It does talk about these different issues and some of the common questions that we get. So have a look at that in detail. It does talk about how you model grates and how those would be included in the model. So I think you'll find a lot of those questions are covered there. So on this particular situation, if we have a grate overflow, what we might want to do is also route that to secondary, just so we can see how much is going out the grate. And now when we do that calculation for, I think, 11P, we have a new line being generated for our secondary outflow, but it's 0 because we are never getting up to that grate. We have a peak elevation of 101, but in fact our grate is up at 110. So we'd need a lot more water before we would hit the grate. And then we could decide where that grate flow is to be routed. It might be that it is through a gutter that's going directly to the next node, in which case we could route them together, and then we are getting those two superimposed arrows indicating that primary and secondary are being routed to the same place. Or it might be that it has a completely separate routing. It may overflow somewhere else and go down a channel, and then perhaps even rejoin the system somewhere downstream. So we can do that kind of diversion of that overflow if we want to. So that is essentially the material I wanted to cover today on pipe modeling options in HydroCAD. As you can see, it ties into quite a lot of different topics, and you will find more information on all of this on the website. And of course, if you have other questions, just email us at support@hydrocad.net, and we'll be glad to help you out with any specifics. I see we don't have any other questions or comments at the moment, so I think I'm going to wrap up today's session. This session is being recorded, and that will be posted fairly shortly on our website. So if you or someone else want to have a look at the session again, you will find it there, in addition to a schedule of upcoming sessions. We should be scheduling other sessions for September and October fairly shortly, so you'll see those on our webinars page on the website. So I thank you very much for joining us today, and I hope we'll see you at a future session. Thank you. Have a great day.